where we left off, we had talked about some of the natural causes of climate change events. First, we're going to talk about the greenhouse effect, and this is a review, quote unquote, hopefully. So, the atmosphere is made of a collection of gases. You probably know the main three are nitrogen, oxygen, and a very small amount of argon. But there's also a lot of other stuff in there that make up that 1%. The atmosphere is primarily clear, we'll call it, or transparent to light from the sun. And some of those gases are also transparent to heat, which means that light that comes in is absorbed at the surface and then radiated back as heat. And some of that heat escapes, but some of the greenhouse gases are not transparent to heat and they trap the heat. And this is not inherently a bad thing. Greenhouse effect allows our planet to be livable. If there was no greenhouse effect, this would be a cold, frozen little snowball of a planet. This is a very simple heat budget. There's a bigger one that I'm going to show you with numbers in it, but just as a quick review, I'm going to try to draw on this. We have incoming solar radiation. This stuff is supposed to be light. Some of the light hits the surface, warms the Earth's surface. Some of it hits cloud and is reflected back. Remember albedo. Some of it hits the surface and is reflected back. That's also albedo. And then when this stuff, this should sort of be connected. Some of it is radiated back to space in the form of heat, and some of it is trapped by the layer of gases that radiates heat back towards the Earth. So that's the greenhouse effect in a simple nutshell. And the reason why it's called the greenhouse effect, this picture's from your book, is because a greenhouse, like you grow plants in the glass, is supposed to represent the atmosphere. It's transparent to those short wavelengths of light. And then when everything inside the greenhouse absorbs that light as heat, it becomes longer wavelength. You probably remember from physics that it's like infrared versus like microwave type thing versus visible light. So then it gets trapped inside and warms the whole area. This is the one that's in your book, and this is actually a really good one. I like this one, but I didn't want to show it to you as your first one because there's a lot of numbers going on. But basically, we have all the incoming, which is in this purple color, all the outgoing, which is in this pink color. And if you notice, they add up and equal 100, right? So all of the incoming equals all of the outgoing. Various parts of this change. A lot of people focus on this, like a lot of climate skeptics. Oh, the amount of solar radiation coming in is changing. That's fairly easy to measure, and it's not. So that's kind of not really changing. Amount absorbed in this atmospheric can change. We'll talk more about that when we talk about the greenhouse gases. But where we see the biggest change, and the one that is kind of scary, is the amount absorbed back heat by clouds, CO2, and to a lesser degree, ozone. That's where we're seeing the change in the Earth's heat budget, and this number emitted back, this 40-20 number, that's the one that we're concerned is changing and thus warming the planet. So let's talk about the main greenhouse gases. Water vapor. I start with water vapor only because it's the most by volume, but it's actually the most confusing in terms of its effect on climate. So the water vapor, which we're kind of using the word vapor wrong, but it's all of the water that's in the atmosphere, whether it's droplets or clouds or actual water vapor just floating around. But all of the water in the atmosphere, we're going to call for the purposes of class water vapor. And 60 to 85% of the greenhouse effect, depending on where you are along the Earth, is due to that water vapor having its greenhouse effect. Foggy air lets light through, but it sort of traps heat, which is why, like on cloudy days, it can stay warmer into the evening than on clear days. So anyway, there's a positive feedback loop that's related between the greenhouse effect and water. And the issue is, and this is one that's very hard to model, which we will probably practice at some point. And this sort of fuzzy picture over here is supposed to help explain it. So we have an increase, we're starting in our circle here, where we have an increase in air temperature. This is called climate forcing. And what it happens is due to evaporation, there tends to be more water vapor in the atmosphere. So any increase in temperature causes evaporation as well as other sources of water vapor like plants to give off more water vapor into the atmosphere. So that increases. In turn, that also causes an increased greenhouse effect right here. And that increased greenhouse effect can lead to greater air temperature. That's sort of the runaway part that people are concerned about. So water vapor tends to be a response, let me rephrase that. An increase in water vapor in the atmosphere tends to be in response to changes in the temperature of the Earth, and not so much the changing factor. The water vapor is already so large in the atmosphere that to have a massive effect on it on a global scale, like individual events like, I don't know, like volcanism, can't really change the water vapor in the atmosphere enough to have its own positive feedback loop. What has to be the starter for this positive feedback loop has got to be increased air temperature. I'm actually going to do the other ones first and then come back and do CO2. And these are the anthropogenic. I hope you know what the word anthropogenic means. Anthro means man, and genic means like cause or beginning. Anthropogenic means human caused. And when we're talking about human caused, we have to be careful. I'm guilty of this as well. I'm not saying humans invented methane. We didn't. There's natural sources of methane all over the planet. But what this diagram shows is how much of the methane in the atmosphere is there due to human caused events. So hopefully that's clear. So if you notice, and there were some weird ones in here that I always thought were strange. Termites, their digestion, their farts, account for 4% of all the atmosphere, all the methane in the atmosphere. There's also some natural methane exchange between the ocean and marshes, that sort of rotten egg smell. Besides being hydrogen sulfide, there's also methane in that, or that oxygen free environment. There's a lot of methane produced. So all three of these are our natural sources of methane, and they're pretty stable. The number of termites is not increasing enough to have a big effect on this. But if you look at these other ones, methane is frequently released to the atmosphere in large amounts by people. In the United States, cows get a lot of a bad rap for cow farts, and that's what that animal waste is. But also, you'd be surprised how much of it comes from rice cultivation, growing rice, because it increases wetlands. Rice grows in these like marsh areas. And then fermentation, natural gas leaks just give off methane. So methane comes from a lot of different sources. One of the things that's important to note about methane, and there is a table in the book about this, when we talk about those greenhouse gases, you can rank them in terms of volume and also in terms of how strong they are per molecule. So water vapor is very weak per molecule, but it's a very large amount of the atmosphere. Methane is a very small, tiny percentage of the atmosphere, but it has a much greater warming effect per molecule than CO2. This all come back to this idea that there's this ice core. We can actually measure methane directly, any of the atmospheric components, going back almost 1 million years because of this relatively recently found ice core. So we know how much methane there is. And then there's other ones, nitrous oxides, which come from burning fossil fuels, and also CFCs, chlorofluorocarbons. They have one of the strongest amounts per molecule. But CFCs are on the decline. Maybe you've heard of CFCs related to the hole in the ozone layer, but CFCs go up into the upper atmosphere and they rip apart ozone. But they're also a very, very strong greenhouse gas. Ozone's on here, and it's a little bit confusing because you're like, I thought the hole in the ozone layer is unrelated to climate. It is. Ozone is also formed, again, through the burning of fossil fuels and chemical reactions, specifically in the catalytic converter part of your car. Ozone is formed through that process. And ozone, by the way, which is just O3 instead of O2, if it's found at the surface of the Earth, instead of in the upper atmosphere, because it can form little pockets. If it's closer to the surface of the Earth, it can trap more, so it can act as a true greenhouse gas. If ozone's at the surface of the Earth, you may have heard of it called as smog. If you've ever been to LA, it's a real problem out there. The greenhouse gas we're probably going to talk about the most in this class is CO2. And CO2 is not the largest in volume. It's not the strongest per molecule. It's not increasing at the fastest rate. But the reason why we focus on CO2 is that its increase historically, and you go way back in time, has been found to be the key component of changing the atmosphere and leading towards periods of glacial minima or warming ages. So the book is already wrong. There's the diagram in the book, which I'll show you in the next slide, which shows that the CO2 is like around 370. That's already wrong since your book's been published. We hit 400 parts per million. It's typically 180 to 320 parts per million, which is a tiny fraction of the atmosphere. But because it's a greenhouse gas, it has an effect. And this is the famous graph from Mauna Loa Observatory. Mauna Loa is the one that's used most often. It's out in the middle of it's on top of a mountain in Hawaii. It's a really good place to study carbon dioxide because it's at the top of a mountain in the middle of the Pacific Ocean. It's not heavily influenced by highways because there aren't really that many highways on Hawaii. It's pretty high up, so it's not being influenced by winds that are like just blowing it around from cities or neighborhoods. And it's also pretty far from areas of like really large cities like Tokyo or San Francisco. So, and if you notice the red thing is there's a zigzag. I always want to show the zigzaggy one. What that shows is that Mauna Loa is in the northern hemisphere. And that's actually, that red line is frequently called the breathing of the planet. Because in the fall, when all the leaves come down, the plants stop taking up CO2 and all those leaves decompose. And there's this little blip of increased CO2. And in the spring, hold on. Sorry, my dogs were barking. Back to the red line. And in the spring, CO2 in the northern hemisphere goes down a little bit because it's suddenly sucked up by all the plants that start growing again when the spring comes. So that's what that red line indicates. The ones in your book sort of have it smoothed out, which is the black line. But that's why sometimes you see the jagged line and sometimes you see the straight line. This is the classic hockey stick graph that caused so much drama. We'll talk about that when we talk about the controversy of climate change such as this. I do like this graph for one reason. They're very careful to indicate natural record means proxies, which we'll talk about in the next video, and this is instrument record. And we'll talk about what these mean, but basically climate change, the amount of CO2 has been increasing, and we're now well above 400. And in your lifetime, it's not likely to be below that. So that's one of the concerns we have, especially because historically, the Permian, during the Permian, there was the last, about 56 million years ago, a big climate change event, and that was when CO2 got above 380. And I'm going to stop there for this video.